Hello, my name is Kaizet, and I would like to share the structural design and analysis of a long-range electric vertical takeoff and landing aircraft, also known as eVTOL. We named our aircraft Widgeon, much like the bird. Specifically, I would like to take you through the steps we took in order to perform the design, from determining the loads and failure modes on the aircraft to evaluating the crashworthiness thereof. But first, I would like to tell you why this analysis was performed. We did this as part of a project for the design and optimization for a long-range eVTOL aircraft. The objective of this particular eVTOL is to transport 4 passengers for 300 kilometers within a reasonable travel time while keeping it a sustainable means of transport. Furthermore, it was determined by a market analysis that there is indeed a need for sustainable personal aerial transportation for intercity travel that requires minimal infrastructure. To first find out what conditions we are designing for, we determined all of the possible loads that the aircraft will encounter and made a structural design envelope therefrom. Once that was done, we took the maximum load factor, that is the total lift produced by the wing relative to the aircraft weight, and applied a safety factor of 1.5 to it to obtain the ultimate load factor, which is the number you see here. Now, the aircraft could fail in any number of ways, but we compiled a list of the most critical and common failure modes encountered by aircraft and explored each of them. Now, in order to design the structural component of the wing, otherwise known as the wingbox, stringers were used to add strength to the part of the wing cross-section where additional material is necessary to prevent column buckling. As such, a number of stringle geometries were considered, and the hatch stringer was found to be the most effective geometry for a reference wing box. Thereafter, the loads encountered in the wing were deduced, which is shown in these figures, giving the internal shear stresses, bending moments, and torques in the wing. And you can see by inspection of these figures that the loads encountered during cruise are much more critical than those during takeoff. After that, the critical stress for column buckling is computed. The yield stress is taken from the chosen material. I'll discuss that later. And we did this for a variety of wingbox thicknesses and stringer placements as part of an optimization algorithm. The maximum stresses encountered by the wingbox under the loads that I presented earlier with the given geometry is shown in this table here. Now, the wingbox geometry was the result of a structural optimization for a wingbox with minimum weight that can withstand the given loads and not fail in column buckling and overload. However, the fatigue characteristics are also evaluated, and these are important as well because fatigue is one of the most common modes of failure for modern aircraft. Now, in order to perform the fatigue analysis, we determined the ground-air-ground cycle for the aircraft, which is shown in the top left. Feel free to compare it to that of a conventional aircraft in the bottom left. Finally, we made a detailed design of a wing fuselage connector lug, as fatigue most commonly occurs in joints and connections. To compute the number of cycles, the ground-air-ground cycle was decomposed using the rainflow counting method and then later consolidated using Miner's rule once the SN curve was used to calculate the number of cycles for a fixed amplitude load. For the crack propagation, the Paris law was applied, and then the cycles were consolidated using an analogous method to Miner's rule. What we found was that the structure required over 100 million ground-air-ground cycles for crack initiation and over 1 million for crack propagation for a given critical crack length. Therefore, considering we need to fly for over 15 years, it is safe to say, given the validity of these results, that the structure is resistant to fatigue. Now, to select an appropriate material for the structural components of the aircraft, a material cost function was derived and a selection was made across 100 metal alloys. We didn't consider composites for reasons pertaining to their sustainability, but by inspecting the lower left figure, we could find that aluminum was the best metal for this purpose, and most aluminum alloys perform similarly to one another. That is why the best material selected for this purpose was 7075T6 for most structural components due to its corrosion resistance and high tensile strength, and 2024T3 was selected for the skin due to its corrosion resistance and the fact that the tensile strength is of tertiary importance for the skin. Now, I would also like to discuss the crashworthiness aspects. You can see in the figure on the left-hand side that most people are able to tolerate accelerations of up to about 20 g in a time frame of about 1/10 in a second. In order to keep this limit, the landing gear is designed to tolerate 8 g and the energy absorbing structure is created to tolerate 11 g. The energy absorbing structure is designed to be crushed upon landing, which is why it's made out of aramid honeycomb structure, and with the dimensions as shown in the figure on the right, it was computed to have a mass of about 5 kilos. Then the landing gear was designed using the model derived from the free body and kinetic diagram from the figure on the top left, which was then converted to state space form and evaluated programmatically. Then the spring constant and damping ratio for the landing gear was configured to yield the maximum vertical accelerations that you can see in the bottom figures. So the landing gear is indeed able to take 8 g of acceleration. Now, I would like to discuss wing divergence, which is essentially the failure of the wing due to torsional and vertical deformations caused by aerodynamic and inertial loads, leading to an unsteady oscillation. To model this, we used a vertical and torsional spring as shown in the bottom left figure, and this was then put into state space form and also solved programmatically. And this yielded the following result that you can see on the right-hand figure, that the motion of the wing during dive, that is the highest attainable speed of the aircraft, that wing divergence is not a critical failure mode due to the stability of the oscillation. This is furthermore exemplified by the left figure, wherein the divergence speed is well above the dive speed, which is about 90 meters per second. Now, the same cannot really be said about propeller whirl flutter, which is the unsteady motion of the propeller about its pitch and yaw axis. To design a structure that is stable in whirl flutter, a steel tube was used to mount the propeller to the wing, which is stable for an angular velocity of 4,000 RPM, but not for 2,500. And this is primarily attributed to the gyroscopic stability of the propeller. Now, to estimate the weight of the aircraft, we used data from previous eVTOLs and applied linear regression to find a trend for payload and empty mass compared to the maximum takeoff mass. For the subcomponent level estimation, we used Raymer's method for general aviation aircraft, which is relatively inaccurate considering the configuration of the eVTOL is anything but conventional. After the preliminary design, several alterations were made in order to increase the level of detail in the design. Firstly, the thickness distribution along the span was made to vary linearly in order to save weight towards the tip where generally lower loads are encountered. Also, the wing rotating mechanism, that is the circular shaft that was carried the loads encountered by the wing, is also designed for shell buckling, which is the critical failure mode in this case. The final dimensions for this circular shaft are also provided here. Now, while this is a good basis for the design, we still have a long way to go to see the widgeon spread or more precisely rotate its wings. We do require additional knowledge on the wing rotation mechanism, but we also might want to improve the validity of our models by using more analytical methods, semi-analytical methods, or even finite element analyses in regions of high geometric complexity. Also, we may choose to explore other weight estimation methods than the ones I showed you before in order to get a more precise estimate for the subcomponent weight. Lastly, while we did take crashworthiness into consideration for the whole aircraft, the accelerations endured by each structural component and their corresponding energy absorption is yet to be determined. And with that said, I would like to thank you for watching.